Mic working okay? Yep. So this is, I think, more than 1 year. I have a live audience, so I'm very happy to be here after 1 year of Zoom calls. So if one picture speaks 1,000 words, I think this is a picture that pretty much tells the story of taxi industry for the past almost 6-7 years. And it's not a good story, it's a horror story. So if you are a taxi fleet owner. So we look at two different metrics. The first is the number that's in blue. You see that over here, this is the average daily trip, steadily going down. On the left-hand side, this is the number that you're actually seeing. I think two major events actually happened during the past almost 10 years. The first is the entry of Grab and Uber. That's around year 2015, 2014. And since then, you can see that it's a steady downwards. And of course, the COVID last year really decimated the whole industry, which is illustrated by the dip over here. And the second thing definitely you see is the constant dropping of the fleet size. Now you see that the whole fleet actually is shrinking in size. To the one point, it's actually very close to almost 30,000, but now it's roughly half the size. So what we propose when we initiate this particular project, what we have in mind is to serve taxi industry. Of course, I mean, if we later you see the technology, you'll see that it should apply not just to the taxi industry, but more generally, any services that's providing point-to-point transport. Potentially, it can be assisted by this technology. But at that time, we focus on the taxi industry because we feel that this is the industry that doesn't really adopt sufficient amount of state-of-the-art technology. So one of the things that we constantly observe is that there's always a mismatch between supply and demand. Certain part of the city you have more empty taxi, but certain part of the city you have much higher level of demand than the other area of the city. The key over here, of course, is to real-time sensing them and then bringing the supply to the area where you really need them. So this is basically the project that we proposed at that time to LTA. The project started probably roughly around 2015. And then we have the data set. I mean, LTA at that time kindly agreed to provide a data set because that was roughly beginning of the data collection exercises they imposed on all the taxi fleet in Singapore. So at that time, what they instruct all the taxi fleet operators is that at an interval of around 30 seconds to 1 minute, taxi in Singapore, they have to provide their real-time location and status to the LTA server. And based on this particular real-time information, of course, I mean, from this information alone, you cannot do a lot. So we have to process it. It contains potentially a lot of errors. You have to correct that. And then with corrected data, you can sense where are the demand. What's the demand channel? Is the demand coming in through street hail, taxi queues, or bookings of various different type? Initially, it's just official booking. It can be booking coming from Comfort or SMRT, so on and so forth. But later, when Grab come into Singapore market, you also have the third-party booking. For example, Grab Taxi initially allows you to actually utilize the vacant taxi fleet for the ride-hailing services as well. But the most important thing comes after that, right? So I mean, of course, doing all this data analysis is interesting, but we want to turn it into action. And this is the focus for the today's talk. We want to see how you can utilize this real-time sensing, this kind of real-time understanding of imbalances, and then you turn it into the action that can help drivers identify which part of the city is the best part of the city to be in. Okay, so this is the very high level. After we have the data set, you can do a lot of different kind of descriptive analytics, basically helping you to understand situation on the ground, both from the demand side, which is this is a typical 24-hour of a working day. You can see that different time of the day. What is the major sources of demand? And on the right-hand side, this is the supply analytics. So you can actually see how drivers are coming onto the road. How are they contributing their time? Are they spending their time on the road efficiently? Are they spending the time of the road in an unwise manner, so on and so forth? Of course, this is just a very high level. If you wish, we can definitely drill down to the region level, time level, driver level, so on and so forth. But I think the real thing that's really motivating this whole branch of research is the analysis of imbalances, right? The first information we see is on the left-hand side over here. So this is actually quantifying and visualizing the imbalances across the whole Singapore. Every dot over here represents one region in Singapore. And as the time you see over here, this is during the morning peak hour, 8 to 9 in the AM. So what you see over here is that y-axis represent the demand, right, of a particular zone. And the x-axis over here represent the supply. So ideally, you want for all the region, this is fraction of demand, this is fraction of the supply. You want all the dots to be falling along this balanced line, this equilibrium line. But of course, you can see that the more chaotic the situation on the ground is, the more divergent those points will be from the equilibrium line. So this first diagram over here at a very high level visualize the imbalances I talked about earlier. The second graph on the right-hand side illustrates that although drivers on the ground, they suffer from imbalances, those sufferings are not equal. Some drivers actually are doing pretty well, right? So what you see over here, this is almost like a normal distribution. This is the normal distribution of the daily income, right? So you can see that it's kind of small, but you can see that the average income is at the level of around $80 to $90 per day. But the distribution is very wide. You can see that for the lower quadrant of the drivers, they are actually losing money, taking into account that they have to pay daily rental, they have to pay for their fuel costs. So every day they just drive onto the road, they are losing money. And on the right-hand side, you can see that some drivers, they can earn up to, for example, $300 and plus, right? So great disparity. But more than that, right? If you drill down deeper to find out what is the driver, what is the potential reason that can explain this disparity, we come up with these three different numbers. These three different numbers represent how sophisticated drivers are in terms of performing strategic reasoning, right? So this is what we call the strategic reasoning level in the behavioral game theory. Essentially, one way to understand it is that if your level is 0, it means that you will just randomly pick available action. You have no idea. If you are level 1, you are always best responding against level 0 opponent. If you are level 2, you are always best responding against level 0 and level 1, right? So the higher the level, it means that the variety, the sophistication of your opponent that you can take into account are also higher. So again, over here, I would like to emphasize this is correlation, this is not causation. But from the data, we did see that for the driver who demonstrate higher level of reasoning, they manage, I mean, from the data, they seems to be earning more, right? So one of the hypotheses that we made at that time is that by using computation, by using computational power, we can definitely generate, in the ideal case, a driving strategy that's of infinite level. This is what we will get if you use Gantt theoretic model. But of course, in reality, people cannot do that, right? So what we want to do is to bridge the gap. We calculate what is the best solution you can come up with infinite reasoning level. And we deliver to the drivers. So you can see that even the best driver, on average, their reasoning level is less than 2, right? So this is the strongest motivation, the visual reason why we are going to do this driver guidance system. So when we look at literature, I think the work mostly assume that it's either single agent, means that you are generating policy for a single user, or it's always assumed that all the drivers are under your control. But in reality, it's always somewhere in between, right? And our model actually addressed that. Second is about demand prediction, right? So one big thing regarding control and the guidance is that you must have the ability to predict what will happen 20, 30 minutes down the road. Where will the demand emerge? Can you use the real-time information to generate accurate prediction? Final part is, of course, we actually conducted the field trial. This is really what makes our research different. We conducted trial in both Singapore and also Tokyo. And in both cities, by using real drivers, we demonstrate the realistic benefit of using this kind of technology. Okay, so these are the three components we mentioned. We have to do stream data processing in real time, handle all the noises that comes with the real data. We have to predict the demand, we have to predict the supply, we have to generate the guidance, which later you will see is quite a large scale and difficult problem to solve. So the demand prediction. So this is the part, again, due to the time constraint, we cannot go into the full detail, but this is one of the, I think, recent advances in making demand prediction by using deep neural network. And I think one of the major design that we follow is that it actually allow us to integrate three different levels of information. We have the special information. Where are the demand, where are the current supply? We encode that into an image. And then we use the image, use the neural network that's able to process the image to come up with the prediction for this part of the information. For the second part of the information, we basically handle all the time series. It can be exogenous, for example, temperatures, rainfall, you have the thunderstorm in some part of the city, so on and so forth. That kind of information can be incorporated using time series. And the final information, and this is the major new innovation we introduced, that basically incorporate the micro movement of the taxi, right? So again, the key idea over here is that traditional method mostly look at the realized demand. When demand happens, you have data. So when you build the demand prediction, you rely your prediction on that. But what we say is that all the cars, all the taxis moving freely within your transportation network, they are providing information as well. Even in the cases that they are not being turned into a higher taxi, they are still telling you something. When they drive, for example, drive by a taxi stand without being converted into a higher taxi, it actually tells you there's no passenger waiting over there, right? So that kind of hidden information is what's been missed in the previous work, and we actually incorporate that by analyzing the micro movement of the vacant roaming taxis. Right, so over here, this is some of the result. I think the key statistic is over here. You can see that the baseline we are comparing our method against is this a DMVST method. This is proposed by, I think, researcher at DD. At that time, when we come up with the work, that was the state of the art. So our method, by combining all the sources, turned out to be working very well. And depending on the congestion level, the higher the level of the demand, the better the performance of our prediction method, right? So this is component number one. The second, also very important component, is to combine information from both the demand and the supply side and generate policies, time-dependent policy, and also region-specific policy to tell individual drivers what to do. So there are three major information that we have to take into account. The first thing is the immediate movement. The second will be expected future revenue. And the third part will be the future movement cost, right? So basically what it means is that when we tell you specifically to move to a particular region, we consider what will happen when, if just so you're lucky enough to be hired, you move to other region, we consider this future potential probabilistic movement as well, right? So essentially, you can imagine this is a very large optimization problem contain multiple periods. Yes, you have a question?
Yeah, yes, I'm just curious for the demand prediction model. for the demand prediction model, if you use the zip code and the time of the day, how bad is the model if we use that as a baseline?
All right, so yeah, I didn't really mention it, but in the special information, actually for each and every location, we have this 3-dimensional image that's constructed. So we divide Singapore into grid size of 1 kilometer by 1 kilometer. Roughly speaking, we have 500 such grid that's humanly inhabitable in Singapore. So each and every one of them, we have this one block over here. So that's how, why this is so computationally intensive. You have to actually come up with the training for each and every grid.
Right. So my question was, so if we divide the data into zip code and timestamp level, what is the baseline that you get, the baseline model? If you build a simple...
You cannot really do it at the postcode level because it's just too little data that will be available. That's why we still have to aggregate them to 1 kilometer by 1 kilometer.
I see. So how does it compare with, let's say, a simple linear based model?
So if you're really interested, that we can take the discussion
Sure.
offline because I think time is limited. But yeah, definitely happy to answer those questions later.
Right. Yeah.
Okay, so this is the predictive prescriptive analytics, essentially taking into account supply and demand information and generate policy. Okay, so after we combine all of that, we need a way to deliver the solution. And this is the mobile app that we designed. We are not professional app developer, so we try to make the app as simple as possible. Very driver friendly. So essentially, the message we tell the driver is that always follow the red boxes. The recommendation will be automatically displayed on the map as a red box. So if they like the recommendation, they just drive the car towards that location. But if somehow they don't like it, they just drive away or drive whichever direction that they wish they want to go to. After a while, our system, after a couple of minutes, our system will detect that and will generate a new recommendation for them. Right. So again, this is tricky because if you detect that the driver is actually driving towards the recommendation, you don't want to change anything, right? But if you detect that the driver is actually not interested, is driving away, you detected that particular intention, then a new recommendation should be produced, right? So this is a major difficulty in designing that. Okay, so the major innovation, I think, in terms of the modeling, particularly the decision-making component, is that we actually consider, as previously mentioned, all the taxis that's not under the guidance, right? So we say that our model is somewhere between single agent and full control, right? So this is what makes the model slightly more complicated. The second part is that we can actually generate a lot of demand scenario to incorporate the potential uncertainty in the demand pattern. And the guidance is generated, again, based on the discrete regions that we come up with. For different cities, that unit may be different. But for a very dense typical Asian city such as Singapore, I think 1 kilometer by 1 kilometer is the reasonable size for the customization. And finally, in terms of solving the model, our solution interval is actually very, very short, only 1 minute. So we have to ensure that our solver is fast enough to finish the calculation for up to 20,000 taxis within 1 minute, right? So again, as mentioned, very large optimization problem. So we utilize vendors decomposition to solve it efficiently. So the most interesting thing after we run the field trial is that we started a field trial in 2017. We recruited eventually around 500 drivers. Of these 500 drivers, 10% of them are active users. So after the usage, what we see, what we try to measure is the amount of reduction in their vacant roaming time. And that time, that reduction on average is 34%. But as you can see from this diagram over here, this particular reduction in the vacant roaming time is not uniform. You see that during the 9 hours where the demands are less predictable, and then again, it's much more difficult to find demand. You see the difference between the unguided one, non-DGS one, and the DGS one, which is the guided trip, are much larger, right? But during even during the morning rush hour where demands are abundant. Always, we see that by following the guidances, you can have much shorter vacant roaming time. So essentially, this technology, by following the guidance, you will always lead to a lower roaming time. Second, we try to break down the effectiveness by areas, right? So this is the area map of the whole Singapore. Again, we try to present this information in the three-dimensional histogram. So what you see over a bar chart, sorry. What you see over here is 2 bars per region. For every region, we actually summarize the performance of drivers following and not following DGS. Again, lower the bar, the better. You see that blue bar over here give you the DGS performance, while the red bar here indicates if you're not following, how well you will do. In all the regions that we are monitoring, following guidances is a better choice. Finally, I think this is the interesting thing that we also discover along the way, is to break it down according to different mode of operation. So as expected, if the taxi drivers is picking up a street hail job, not following versus following, which is this column over here versus this column. By following the guidances, your vacant roaming time can be reduced by 36%. But if you are picking up a trip through the booking channel, again, this booking channel can be coming from taxi fleet operators such as Comfort, or it can be coming from the ride-hailing operator like Grab taxis. Either way, the average roaming time also reduced, although by a lesser degree, right? But it's still reduced by 23% roughly. So this is the first number that we see. So DGS is effective for all the mode. But another interesting information I would like to share is that there's a misconception that booking definitely will be more efficient. But if you only look at the vacant time, booking is not necessarily more efficient than street hail, because on average, the vacant roaming time for street hail is around 12.8 minutes, close to 30 minutes. But for booking, although the vacant roaming time is only 9 minutes, but after the taxi driver accepts the booking call, he still have to move without passenger to the pickup location. This is what we mean by the response time. This is on the way to pick up. And this number is constantly at around 5 to 6 minutes, which is pretty efficient. This is the time at the moment when you get the driver assigned to the moment that the driver can finally pick you up. So the summation of these two numbers is the actual vacant time. When you take that into account, actually booking is not so much better than the street hail. And the more important of all is that if you look at DGS, the vacant time we calculated per trip is only 35%. While if you look at the booking, right, the vacant time per trip is up to 43%, right? So I think that the last takeaway message over here is that when we run the trial, if you are able to push this technology to the user, even the user are already using the booking technology, their performance, regardless of their source of the job, can still be better than the case of the booking that's coming from the platform. Okay, so finally, initially our trial is only in Singapore, and as mentioned, as summarized, the reduction in the vacant roaming time is around 34%. So just last year, when COVID is just beginning, we also conducted a trial in Tokyo. So this is with the help from our industry partner, Fujitsu, who at that time supported our corporate lab effort. They put us in touch with the second largest taxi fleet in Tokyo. And this time, they actually hired around 30 dedicated drivers, 29 to be exact. So the major difference between this trial is that in the trial that's happening in Tokyo, we have full-time driver following the recommendation. They have no choice, they have to follow 24 hours, right? So resulting reduction in the vacant time, roughly speaking, is 12%. Right. So again, this is initial trial, only 1 week. It's not conclusive, but at least it demonstrates that the guidance technology, when calibrated for different cities, it also works. The magnitude, again, there's so many different external factors at play. It's hard to say whether or not it can be better or it can be worse, but this is the baseline that we can work with. And 10%, more than 10%, this is the non-trivial improvement. And again, for the Tokyo trial, because we are working with the fleet directly, we can actually anticipate what will be the financial impact of that reduction. And for every 10% increase in the vacancy, it will reduce the average fare for the driver by more than 600 yen. So that is how we can actually quantify the financial impact of not having this particular DGS technology. So final conclusion over here, again, we apply a lot of different type of analytics in this project. Descriptive, this is high-level analysis. And then we do the predictive analytics. We do the prescriptive analytics. And I would say that this is really what's making this particular research project different. We actually use that in the real world, observe the real benefit experienced by different drivers in different type of market. So looking forward, I think this field trial part of it is pretty much concluded. But in terms of research, what we are looking at right now is how we can continue to utilize this type of technology, assisted technology, for any kind of real world task that involves drivers' ability to infer the competition on the ground. Whenever you have this kind of situation, we feel that the DGS type of technology should help the performance at both the individual level and also at the fleet level. The second thing I think also interesting is that although it's commonly believed by a lot of people, including regulator in Singapore, they believe that eventually booking-based technology, which is ride-hailing platform in most cases, will be the dominant choice to serve the point-to-point transportation demand. But this may not be the most efficient way in serving the demand, as illustrated by one of our analysis. We see that for the book trip, but that's not guided, you actually have 43% of vacancy still, right? But if you have a guided, even though the technology-wise is less advanced, is street hail, you can only have, you will be able to achieve only 35% of vacancy. That turned out to be more efficient than the book trip, but unguided. So positioning driver at the location they are needed turned out to be more important than the matching technology, which is whether or not you are using the ride-hailing platform, right? So this is the final takeaway, and we are still doing research on that. So I think at this point, I will conclude my talk.
Thank you. Any questions?
Hi, can you hear me?
Yep.
Shih-Fen, yeah. Thank you for the very interesting talk. And I'm thinking one of the things that you provide, you can reduce the information asymmetry, right? Because you have a centralized system, right? I was thinking that perhaps if you just consider showing information about a heat map, so you do the predictive model rather than demands, and somehow use this information without doing the prescriptive, right? How would that? So in other words, you let the real agents do the optimization rather than to assume a model that
yeah, very good question. That was actually the status quo. If you look at it, like Grab does that, Uber does that, even Comfort does that.
I see.
And then whenever you let individual agent do that without recognizing, because I think the most important misinformation in the demand hotspot is that you don't have supply side information.
Correct.
Yeah, so that is the critical missing consideration in this kind of approach.
Okay, but the thing is that when you do the field trial, is it possible to compare the difference between these two approaches?
So again, we didn't really specifically control for that, but we assume that actually that kind of information is available for drivers.
I see. Okay, thank you very much.
Yep.
Can I ask? Hi.
Yeah.
Nice talk. I was wondering, congestion is an important issue in these systems, right? Congestion. So, congestion would probably drive into your, it could be an input to your model in your driver guidance system, but people using your system will also cause congestion. So where does congestion show up in your modeling framework?
Yeah, so one of the things that we actually consider is the numbers of agents in all the different regions. So in other words, specifically, we already consider what will happen if this particular decision is delivered to like potentially more than one user. So that's why when we make the recommendation, it's not going to be a pure 100% you must go here type of recommendation. It's always probabilistic. It means that if even you and your colleague, for example, your friend are in the same region, potentially you may be receiving different strategy recommendation, right? So we are giving you essentially a mixed strategy. Yeah. But of course, as a driver, nobody likes probabilistic recommendation, right? I will give you a definite recommendation, but when we aggregate those definite recommendations, it reflects the distribution that we will recommend.
Hi. Just a quick question. It's fascinating. The number of layers of data that you put together. Is there any place where this data is available, an anonymized version of it, so that we can use it for research? Or is the API for your service accessible for researchers?
So this project, unfortunately, already come to a close. So one of the major data that's driving this is actually the taxi level data analytics that's provided by LTA. The data set we get from LTA is proprietary, but they actually have an open source alternative that provides only the available taxi. It doesn't provide, for example, those taxi that's currently hired, but it does provide those vacant taxis. And that data set turned out to be useful as well.
Yes.
Yeah, you cannot really train, for example, without demand data, definitely you cannot generate like good demand prediction model. But you can still, if you have some assumption about how demand are distributed, you can still make the guidance model work.
Thanks.
Yeah.
So actually 2 questions. So first, do they actually comply? What do I mean? Like, do they follow the recommendation? So that's first, so then you could use IV, there to really, then second, these 2 groups, are they different? The guys who are using this app versus those who are not, so can you show like, the pre, implementation, how much they, how well they did, just comparing, before the, this test.
Yeah. So I think for first part, definitely we cannot track whoever who signed up for that, and it's only 500. So compared to the whole population, it's much less. And at that time, when we actually run the field trial in Singapore, we actually have incentive. So if their compliance level is about certain percentage, they actually get monetary reward, right? So that's one of the big reasons why they actually follow that. But the second question is that we kind of track at individual level. It's almost like a performance review. So for every participating driver, we actually give them their performance review. This is you not following, and your performance not following this. And this is you, still you, no? But you follow our recommendation. This is your average vacant time. For each and every driver, we show it to them. And this particular, again, the actual performance improvement varies from driver to driver, but is pretty much universal. Magnitude different, but it's always an improvement for them.
Well, I think time is up. Maybe leave. Okay, let's thank the speaker again.